Pluto, once considered the ninth planet in our solar system, remains a distant, elusive, and often overlooked celestial body, although reclassified as a dwarf planet. Pluto has re-entered public discourse thanks to provocative statements by renowned astrophysicists such as Neil deGrasse Tyson and Michio Kaku. They've suggested that Pluto may be on a potential collision course with Neptune, a claim that has sparked widespread intrigue and concern. But how could such an extraordinary event occur? And what would the implications be for our solar system? Perhaps even for Earth? Join us as we explore this cosmic puzzle and the startling theories surrounding a possible Pluto-Neptune collision. Pluto's orbit is anything but ordinary. It takes an astonishing 248 years to complete a single revolution around the Sun. And since its discovery in 1930, it still hasn't completed one full orbit. What sets Pluto apart further is its highly elliptical and tilted orbital path, inclined at about 17 degrees to the plane of the solar system. Unlike the near-circular orbits of the major planets, Pluto's trajectory is eccentric and erratic. One of the most fascinating aspects of Pluto's orbit is how it crosses Neptune's path. For about 20 years during each orbit, Pluto is actually closer to the Sun than Neptune, a seeming recipe for disaster. So, why haven't they collided? The answer lies in the delicate dance of gravitational mechanics. Despite the orbital intersection, Pluto and Neptune never occupy the same space at the same time, thanks to a phenomenon known as orbital resonance. Specifically, for every 3 orbits Neptune completes, Pluto completes 2. This 3:2 resonance ensures that the two bodies are always at least 90 degrees apart in their orbits when Pluto is nearest Neptune. Another key stabilizing factor is orbital precession. Pluto's orbit slowly shifts over time in a vertical motion, which means that even when Pluto comes close to Neptune's orbital path, it does so either well above or below Neptune's plane. The spatial separation acts like a cosmic safeguard. Adding to the stability is a lesser-known effect called the Viescay wobble, named after researchers Zell, Sato, and Kai, who study gravitational interactions among celestial bodies. This wobble describes how subtle gravitational nudges from Neptune, Pluto, and the Sun combine to create long-term orbital stability, even in what appears to be a chaotic environment. These dynamics are all part of the larger three-body problem, a complex gravitational relationship between 3 massive objects. Understanding how Pluto, Neptune, and the Sun influence each other helps explain why, despite their overlapping paths, a collision is extraordinarily unlikely. In the late 1980s, numerical simulations confirmed that Pluto's orbit, while seemingly precarious, is remarkably stable over millions, even billions, of years. Rather than being on the verge of disaster, Pluto's path showcases the intricate and elegant mechanics of our solar system, where even apparent chaos is governed by a hidden order. The forces governing Pluto's motion are highly sensitive and somewhat erratic. Even tiny variations in its initial conditions can cause significant changes in its orbital path over centuries. However, simulations have shown that despite the sensitivity, Pluto's orbit remains remarkably stable over extremely long time scales, spanning millions or even billions of years. To fully understand the dynamics between Pluto and Neptune, it's crucial to consider the gravitational influence of the outer giants, particularly Neptune, Jupiter, and Saturn. Neptune plays a dominant role by locking Pluto into a special orbital resonance. For every 2 orbits Pluto makes around the Sun, Neptune completes 3. This 3:2 resonance acts as a stabilizing mechanism, preventing close encounters between the two bodies. But Neptune isn't the only influence. Jupiter's immense gravity also contributes to the long-term stability of Pluto's orbit, while Saturn adds to this intricate gravitational dance. Together, these giant planets create a balanced system that keeps Pluto on a predictable course and safely out of Neptune's path. Without these stabilizing forces, the solar system could be far more chaotic, with planets potentially veering off course or even colliding, events that could trigger catastrophic consequences. The possibility of a future Pluto-Neptune collision, despite the current stability, underscores the complexity of celestial mechanics and the importance of studying orbital behavior over time. Understanding these dynamics enhances our grasp of how the solar system functions, the role of gravitational interactions, and the delicate balance that governs distant celestial bodies. Although Pluto's orbit might appear chaotic, It is actually a prime example of how cosmic order can emerge from seeming randomness. The concept of orbital chaos refers to how even minuscule changes in a celestial body's position or velocity can dramatically alter its future path. Automated simulations allow scientists to explore these scenarios, revealing how Pluto's movement is influenced by subtle gravitational tugs from Neptune and other planets. These models have shown that, while Pluto's orbit is stabilized through mechanisms like resonance and precession, it's still sensitive to slight variations. This makes long-term predictions difficult, but also highlights the extraordinary balance that keeps Pluto in check over geologic time. Predicting the motion of objects with such complex orbits is a daunting task. Small errors in initial measurements can lead to widely divergent outcomes, emphasizing the uncertainty in long-term forecasts. Still, studying Pluto's behavior offers a powerful reminder of how dynamic and ever-evolving our universe is. Despite everything we've learned, Pluto's orbital story shows there is much we still don't fully understand. By examining how the giant planets influence Pluto's trajectory, we gain deeper insights into the interconnected mechanics of our solar system. So why, then, are renowned astrophysicists raising questions about the potential for a Pluto-Neptune collision, even with all these stabilizing forces in place? Neil deGrasse Tyson, a leading voice in modern astrophysics and a key figure in Pluto's reclassification as a dwarf planet, offers a compelling perspective. His insights remind us that, while current models suggest long-term stability, the cosmos is full of surprises, and Pluto's future remains an open question. The perception of Pluto and its role in our solar system has evolved significantly, especially in light of new discoveries and shifting scientific perspectives. Neil deGrasse Tyson, a prominent astrophysicist, views Pluto's reclassification not as a demotion, but as a necessary refinement in response to our growing understanding of the cosmos. For Tyson, celestial mechanics is a field defined by constant exploration and change. He sees the intricacies of orbits, like Pluto's, as evidence of how much we have yet to learn about the universe. While Tyson remains hopeful about the progress of space science, his comments on the possibility of a Pluto-Neptune collision highlight just how many unanswered questions remain. Could such a collision truly occur? Or is it simply a misunderstanding within a complex and ever-evolving celestial system? Only time and continued research will bring clarity. For now, the possibility sparks even greater curiosity about the mysteries that still surround our own solar neighborhood. The notion of a Pluto-Neptune collision raises important questions about planetary dynamics. If two such distinct celestial bodies, Pluto, an icy dwarf planet, and Neptune, a massive gas giant, were ever to collide, it would have far-reaching implications. It would challenge our understanding of gravitational interactions and offer invaluable insight into the processes that shape our solar system. To fully grasp the dynamics of potential impact, it's essential to consider the nature of both planets. Pluto, residing in the frigid outer reaches of the solar system, is made up of frozen nitrogen, methane, and carbon monoxide, both on its surface and in its thin atmosphere. In contrast, Neptune is a colossal gas giant composed mainly of hydrogen, helium, and other lighter elements, with a dense and turbulent atmosphere. A collision between these two vastly different bodies would be catastrophic, an event likely visible across great cosmic distances. However, such a scenario remains highly improbable. While Neptune's gravity plays a major role in influencing Pluto's orbit, it is not the only factor maintaining stability. Jupiter, the solar system's largest planet, also exerts significant gravitational pull, helping keep Pluto from drifting too close to Neptune. Saturn's influence adds another layer of complexity, contributing to the intricate gravitational balance in the outer solar system. Pluto and Neptune share a unique orbital resonance. Pluto completes 2 orbits for every 3 of Neptune's. This 2:3 resonance acts as a built-in safeguard, ensuring that although their paths cross, they never actually collide. Often referred to as a gravitational dance, this mechanism is a remarkable demonstration of how order can emerge from apparent chaos in the cosmos. Yet, this delicate equilibrium is not set in stone. Minor changes in velocity or orbital positioning, whether caused by external factors like a passing star or internal ones like tidal forces, could disturb the resonance. Even slight shifts might result in significant and unpredictable consequences over astronomical timescales. Continued observation and advanced simulations are vital for understanding the long-term stability of this relationship. As technology improves, astronomers will be better equipped to model these interactions and assess the potential for future changes. New discoveries may confirm the resilience of Pluto and Neptune's orbital resonance, or reveal unforeseen forces that could alter their paths. One such unknown is the theorized Planet 9, a hypothetical large object believed to exist in the distant solar system. Some scientists suggest that its gravitational influence could affect the orbits of trans-Neptunian objects like Pluto, potentially nudging them onto new trajectories. Although Planet 9 remains unconfirmed, the possibility of its existence adds another dimension of uncertainty to the system's stability. Adding to this complexity is the gradual evolution of the solar system itself. The Sun, as the central gravitational anchor, is slowly losing mass through solar wind. As it does, the orbits of all planets, including Pluto and Neptune, may expand slightly over time, altering their spatial relationships and possibly affecting their long-term resonance. Moreover, the outer solar system is far from static. It is populated with countless objects, comets, asteroids, and icy bodies that occasionally pass through and exert their own gravitational forces. Though rare, such interactions can disrupt planetary orbits in subtle but meaningful ways, reinforcing the idea that Pluto's journey is far from fixed. In the end, Pluto's dynamic orbit reflects the intricate gravitational choreography of the outer solar system. While a collision with Neptune remains highly unlikely due to the stabilizing effects of resonance and the influence of larger planets like Jupiter and Saturn, the system is not immune to change. Our best path forward lies in ongoing exploration and observation, continuing the quest to understand not just Pluto and Neptune, but the vast, interconnected mechanisms that govern our solar system.